Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Laplace Transform Convolution Theorem. Alright, we're going to motivate this formula a little bit with an example, and so we're motivating the formula for the inverse Laplace transform of the product of two functions of S. So let's consider the first order initial value problem shown here, and we're going to solve this not using Laplace transforms, and I kind of using integrating factors here, but you see we don't know what f of t is, so when we solve that we end up with a solution, and you should work through this, but y of t is equal to e to the at, and this is the integral from 0 to t, e to the minus a tau f of tau d tau. But now this does not depend on tau, so I can shove it inside the integral, do properties of exponents, and I get this. Now, so since we don't know what f of tau is, or f of t is, that's all the further we can go. But we solve this using integrating factors. And by the way, you've seen this kind of thing with the t minus tau happening before. We saw that in some of the Green's functions. So we solved it, and we got that. But now we're going to solve the same equation. The same equation is up here. We're going to solve it using Laplace transforms. We've done this a lot. So when you do Laplace transforms, you get this. And here you get, we'll solve for y of s, and you get that. You're using the initial value there. And so the inverse transform is going to be the inverse transform of these two things. But in our problem, g of s was 1 over s minus a, and that is the same thing that we saw on the other page. So that is f times g, and so the solution is the inverse Laplace transform of fg. But on the previous page we saw it was this. So you see what we're saying is that the inverse transform of fg is going to be the convolution integral of y of t. Now that didn't prove anything, but that was okay. That motivates our definition. The convolution f star g of two functions f and g is defined this way. It's a function of t, and the t is an upper limit here, and the t is also in this equation. And it is a nice exercise for you to show that f star g is the same thing as g star f. That's a change of variable, and again, a good exercise for you to work through. But now we come to the main convolution theorem, and we say if the Laplace transform of lowercase f is uppercase f, and Laplace transform of lowercase g is uppercase g, then the Laplace transform of the convolution is the product of the Laplace transforms. Or, said another way, the inverse transform of the product is the convolution. And this is manifest in our table with formula 33. That's what formula 33 says right here. And that tells you going both ways. Let's look at the proof of this. Now, this is not a completely rigorous proof, because we would have to show that the Laplace transform of this actually exists. But we're just going to assume that it exists and do the calculation. So Laplace transform of the convolution is, here's the e to the minus st integral from 0 to infinity dt, and I just put the convolution there, but now I'm going to write what the convolution is in terms of its definition. So it is going to be the integral from 0 to t f of tau g of t minus tau d tau dt. And now, as so often happens, what we're going to do is change the order of the integration. First we're integrating with respect to tau and t, but we can invert that order of integration. So now we're going to do it with respect to t first. And so when we do that with respect to t first, you see the t is now the first integral that we do, and we're going to use this schematic to help us figure out the limits. But we get that the Laplace transform of f star g is equal to the integral from 0 to infinity f of tau, and then this is the integral from, this is going to be from tau to infinity, e to the minus stg of t minus tau. Now we're going to do a substitution with this part of the integral. We're going to let x equal t minus tau. So if I do that, I get e to the minus st is there, but then I'm going to call this x, and again t is going to be x plus tau. So we get that, and the limits of integration change, because if I start at tau, this goes from 0 to infinity. So I get this expression, but the e to the minus s tau doesn't depend on x, so I can pull it through the integral. I get this, and what this is nothing more or less than the Laplace transform of g. So I have this is what this was. So now I will plug that in here, and the g of s doesn't depend on tau, so I can jerk it through the integral, and I get g of s times f of s. Okay, so here's an example for you to do. Evaluate this convolution integral. You know what to do. Let's see how you did. Well, that would have been a pain to evaluate that in powers of tau. It could be done, but the easier way is to use the convolution theorem. So we know that that integral I asked you to compute is the convolution of f of t being this and g of t being that. So now I'm going to look at the Laplace transforms of each of those, and the convolution theorem says that h of t is associated with the product of their convolutions. Now so I get this because s to the 6 times s to the 8 is s to the 14, but then here I'm grooming this so I know how to take the inverse transform of this. I have to multiply top and bottom by an enormous number of 13 factorial, but I do that, and then what I can do is I can invert the transform and get t to the 13. So you see, the answer to this problem is h of t is that big number there times t to the 13. Here's another one. Use the convolution theorem and a partial fraction expansion to evaluate this convolution integral. You know what to do. Let's see how you did. Now, it will be important the absolute value of a does not equal the absolute value of b, as you see, but again, that's a convolution interval, so we're going to look at the transform, and so we know that the sine has this as its Laplace transform, the cosine has this as its Laplace transform, and so we know the transform of the convolution is this. Now, I have to do partial fractions on this, and that will require a squared to not equal to b squared. But we do the partial fraction. That's a common constant that we have, and this is what we have left after we groom this. And now we will invert this transform to find out what h of t is, and h of t is going to be the same constant, and that is e to the at minus cosine bt. Last example we'll talk about here is an equation of this form. Y of t is equal to f of t plus the integral from 0 to t of k of t minus tau, y of tau d tau, is called a Volterra integral equation named after Vito Volterra. Now here f and k are given functions and y is unknown. But since the integral on the right is a convolution integral, the convolution theorem provides a convenient formula for solving this. We take Laplace transforms, we're solving for y, so we get y of s is equal to, this is f of s, and that's the product of these two. So I can solve this for y of s. I get y of s is equal to this expression, and so that means that y is equal to the inverse transform of that. Here's a problem for you to solve, and it again is a Volterra integral equation, so you know what to do. Let's see how you do. I guess. So you take Laplace transforms everywhere, you get this. Then you do algebra to solve for y of s, and then you groom this a little bit so it's things you know how to take the transform of. Then you use your inverse transform, and y of t is 1 plus 2t. In closing, now more than ever, time is precious, each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.